Hello, everyone. Hello, everyone. So first of all, I'd like to give all of you attending here a very warm thank you. I think that matches the weather we have today. So my name is Xiaohong Chen. I'm the CTO of Pi2. So welcome to today's workshop. So we have a great team attending. So we have our chief architect Yi, team lead staff researcher Elias, and two very skillful developers, Chenlong and Video. So we have a 30-minute presentation ahead, and we'll use the first 20 minutes to go over Pi2's mission and vision, and also talk about the universal language machine. One of the many products we are very excited about. And then I'll pass the stage to my team, who will be giving you two demos. We will have some time at the end for questions, but if any questions or comments during the presentation, just let me know. I'm very happy to have a discussion with you. So without further ado, let's get into the topic. So Pi2 is unique as the world's first modular universal protocol. Okay? And this protocol brings three core, highly valuable benefits. First, you can program in any language. Second, you can settle any type of proof, including zero-knowledge proofs. And three, you can reach lightning-fast generalized consensus. Okay? So let's explore these benefits in depth. First, you can program in any language. So that means Web3 applications and smart contracts can now be written in any programming language, even your own custom languages, right? So you are not restricted to learning particular Web3 languages simply because only they are compatible with a blockchain ecosystem. So Pi2 makes it so any programming language is essentially Web3 compatible. And it is in that sense, it's universal, right? So we are the first protocol that universally supports all programming languages for Web3. Second, you can settle any type of proof, including zero-knowledge proofs. So all the data, transactions, computation can be consistently represented, stored, verified, settled, and used, right? So it's really up to the applications and the users to freely decide what particular proof mechanism they like to use. And that can be from the traditional mathematical proofs to the zero-knowledge proofs in any ZK VMs or ZK backends, to digital signatures, to validation by re-execution, and so on. So the users and applications have maximum flexibility in deciding what proof mechanism they want to use for their apps. Last but not least, we can reach lightning-fast generalized consensus. So traditional blockchains require a very strict total ordering of the past transaction, and that often limits the speed and the scalability. So in contrast, Pi2 enables a much more generalized and scalable approach by dropping the total ordering requirements. So with these three benefits, we are looking at a very massive market opportunity for Pi2 because we empower any developer to build on top of any blockchain. Right? So we all know that chain-specific languages are a major obstacle to the growth of an ecosystem. Right? So take Ethereum, for example, whose ecosystem mostly centered around the Solidity developers, right? Which are about 8,000. And even if we zoom out a bit and look at Web3 in general, the number is about 26,000. So what Pi2 can offer here is to break that growth limit because we can make Ethereum no longer restricted to a small set of Web3 languages. And so we can engage a much larger potential developer base, including those who are proficient in programming in C, Rust, and Python, and so on. Right? So over time, we look forward to open the Web3 world to all Web2 developers, including even prompt engineers, and allowing for an unprecedented growth in the Web3 ecosystem. So how is it possible? How we achieve it? So this is achievable using three major orthogonal innovations that are happening at Pi2. So the first one is the Universal Language Machine, or the ULM. And this is going to be the main topic for today. The ULM allows you to write any smart contract in any programming languages, even your own language, right? And currently we support Solidity EVM, Wasm, and Rust. But we plan to support more languages on the go, okay? The second module, which we call it a universal settlement layer, it's all about proof, right? So it's a common layer where all the applications across blockchains can come and settle their transactions on it. And it supports both mathematical proofs and zero-knowledge proofs. And the last component is a universal consensus, which will not be the topic today, but we'll cover it in the future. So I want to talk a bit about universality. I think we all agree that it's a great term, it's a great feature to have. So we want to be universal so that we can engage more developers out there. So I think the question here is really not why we want it, but why we haven't have it yet. What's the problem? What's the obstacle? There are many reasons, and one of them, the major one, is that programming language create barriers, right? Just like human languages, right? So imagine how many developers, very talented developers out there are at least marginalized, by this community simply because they're not proficient in English. Something similar happens in the blockchain space and the programming language area as well. So what we have here is we have all kinds of languages, classic languages like C, Java, and so on, and also the so-called Web3 languages like Ethereum, EVM, and Solidity. Each programming language comes with various tools, like interpreters, compilers. We use them all the time. And when you want to prove that your smart contracts are correct, you're going to use more advanced tools. For example, symbolic executors, modal checkers, and so on. And the barriers are here, right? The barriers are caused by we have to spend time and effort to develop these tools for emerging languages. We have to maintain them, we have to update them as the languages evolve, and we have to train developers. Right? All this takes time and effort. It's never ending. It's ongoing, keep on going. So we have these huge efforts, huge barriers across ecosystems and applications. How can we break these barriers? So the approach we are taking at Pi2 is using what we call formal semantics. Right? So for those of you who don't know, you can think of a formal semantics of a language as the mathematical definition of your language. Not only that, it is a mathematical definition that is 100% complete, rigorous, executable. Okay? So it defines all the behaviors of all the programs in that language in a mathematical way. So in theory, from it, you can automatically derive all the language tools from the semantics. And this is the semantics first approach we're taking at Pi2. We use what we call a universal language framework to define the formal semantics of all the languages we have and automatically generate language tools once and for all. Okay? And currently we're using semantics called K, but you can use whatever language semantics out there. There are many of them. But the key point here is that we do it by having a separation of concern. Right? We separate language design from tool implementation. So why, so what does it matter to a developer? Well, as a developer, now you can plug and play your language, right? So imagine you are building a Web3 application, and for good reasons, you like to use your custom languages. Well, one of your biggest concerns would be that, oh, I have a lot to do. I need to re-implement tools for my languages from scratch. It's a big effort. Not anymore, because if you use a semantics-first approach, you can simply plug and play your custom language, and you automatically get all these wonderful tools for free, right? And because all these tools are derived from a semantics, a mathematical definition of a language, they are correct by construction. There's nothing to prove about their correctness. They are based on the mathematical definition, correct by construction. So here's an example of what a semantics looks like. Okay, in K, there are stuff going on here, but I want to remind you that this is a complete semantics of a language. Actually, it's a subset of C, with C-like syntax, if statement, and so on. But this is everything. Right? So in 39 lines, you can have a semantics of a language that's working. Right? And of course, stuff going on here, you define the concrete syntax, configurations, what are the states of the program, and a couple of rewrite rules to tell you how to go from the state to the next one, and so on. And this is all open source, right? So the K framework is open source. You can simply go to kframework.org and get a test of the tool. So before I get into the ULM, I want to spend maybe 5 minutes to talk about pi squared. What is pi squared? So pi squared means proof of proof. It's a zero knowledge proof of mathematical proof. And it is a universal verifiable computing framework for all languages. This is how it works, okay? So let's take a look on the left. So what's on the left are the input. You give it a programming language. We have a program and the execution environment of the program. Okay? And then stuff happens. Okay? So there are a lot of stuff, and you will get a ZK proof. All right, then it's a verifiable computing framework. I give up my program, I give the execution environment, and at the end I get a ZK proof. What's unique here is this component. The programming language is now an input to the framework. This is a verifiable computing framework which can take a programming language as input. It's not specific to a particular programming language. It works for all languages. Okay? So I think for this presentation, there are a couple of intermediate states. I think what matters for this talk is the first part. So once we have a programming language, we can automatically generate an interpreter. So let's look at this interpreter. This is probably one of the most important slides I want you to take away with you. Okay? So the interpreters derived from semantics are not only correct by construction, but also fast. I want to say that again, because it's the first time we've seen this result in history. Define the formal semantics, a mathematical definition of your language. You can automatically derive an interpreter. That interpreter is not only correct by construction, but also fast. Okay? So we've run a couple of tests. This is a typical one. So this is a test program that does 1,000 swaps, unit swap. The first line is our baseline, right? So you can compile it into an EVM and then run it with get, right? So the time is 248. Instead, we can run exactly the same program using a semantics-derived interpreter for Solidity. And it's only 5% slower. Switching to a correct by construction semantics-derived interpreters have only a 5% performance overhead. And just do some very preliminary optimizations, we can be 63% faster, right? So all the results actually are public, so these will be available at a public repo. But I want to emphasize this point a bit. It's actually faster to get an interpreter for your language by a formal semantics. Not only correct by construction, but also faster. All right, so now let me get into the ULM, the Universal Language Machine, which is what enables us to write smart contracts in any programming language, even your custom languages. We've seen how we can achieve the best ever universality using formal semantics, right? So by writing a mathematical definition of your language, you define all the behaviors of all programs in that language. And of course, it applies to all programming languages, virtual machines, ISAs, and so on. It has the best ever universality. You can automatically generate interpreters, and they are correct by construction and fast. What else? What's remained? The question here is, how can we build on top of this great technology to have a blockchain that permits any smart contracts written in any programming languages? And in order to do this, there are two key challenges to solve. First, we have all these interpreters, generated from the semantics. There should be a way for them to talk to modify the same blockchain state. And we solve it by implementing the same ULM interface, which my team will be demoing you later. And the second challenge is that all these smart contracts in different languages must be able to communicate to each other. There must be a way for them to interact. And we solve them by making sure that contract calls take place through the embodied encoding. So without further ado, I'll pass the stage to my team. who will be giving you the first demo, where you can really show that how we can build a blockchain that allows you to write smart contract in any languages. Yeah, piece of video.
Hello, everyone. Damien here, and first of all, welcome to our Bring Your Own Language demo, in which we will show how using Pi2 tech you can run multiple programming language smart contracts on the same blockchain with minimal changes to classical EVM. Now, first of all, I want to let you know that we're using a special smart contract called the language registry in order to keep track of all the languages that we have available. Here you can see that we have the EVM only available on chain with a special ID that will be needed when deploying EVM contracts, and with a specific hash that is used to verify the authenticity of the language by validators in order for them to know that they're running an authentic language. If we could also click really quickly on the hash to see the definition of the language. We won't lose lots of time on this, but this is checkable by checking the hash. We can go back now. And what we're going to do first is that we are going to add a new language. Let's first add a new language. We will add Rust first. We can see the definition of it. We can see the name of it. And we can add the new language now. We get a disclaimer saying what's saved on chain about the language. We confirm it. And boom. Now, as we are waiting, when this transaction is done, we have just enabled around 3.5 million developers that are using Rust worldwide to develop on an EVM chain. It is there, we have the ID, we have the hash, we have the definition. Now let's take the ID and actually deploy a contract using Rust. We input the language ID, and whenever we do that, we show the hash and the name of the language to be sure that we actually use the correct language. And let's deploy a wrapped Bitcoin contract. We can see the definition of the contract, and just to be clear, we're not compiling this in any way. We're just hex encoding it and sending it to the blockchain. We have the address of the contract, and now we are ready to interact with this contract. Once we input the address and obviously the ABI for fast interaction, we can load the said contract, and we can see, we can read from the contract, we can write to the contract without any issue. Let's first check our balance so you can see that we have a balance of 0. Okay, our balance is 0. Now let's mint some tokens in order to have a higher balance. We're going to mint 923 tokens. And we're going to send the transaction to the blockchain. We're going to confirm it. And now we can also see the transaction receipt. Like for any transaction, there's all the data there. The contract was deployed, and that's about it. The rest is exactly the same for any developer that integrates it, like for any EVM. Let's read our balance again. 923 tokens, obviously with the decimals after it. And this is about it on what we want to show with Rust. Now, let's also add another language. We will add Simple. Simple is a programming language that we have developed internally. We're using it for testing and to basically show that it's possible to add whichever language. Feel free, let your imagination flow. Just add whichever language you like to. As we are adding Simple, the language is added. We can see it in the language registry as well. It was added. We'll get the ID of it in order to deploy the contract. And as we input the language ID here, I want to emphasize this is the only difference to classical EVM. And what I mean by this is when we upload a contract, what we do is that before the code of said contract, we prepend the ID of the language that we're using, and that's how we that's how the executor of the code recognizes what type of language will be used. Now, let's get the address of the Pi2 token, because what better to deploy in a random language that we have created. We have the contract. We can read from it. We're getting our address again. Let's try this time to allow spending from our address. We will allow to spend from our own address. For now, the allowance is 0. Let's go and write. We will allow 314 tokens and sending it. And what I want you to look at is the fact that basically the transaction is recognized by MetaMask and it's showing what's the spending cap. And it's recognized that it's a usual transaction. There's no difference to classical EVM. Once again, no matter what language you use, the persons that are then integrating your smart contracts don't have to care about your programming language. We have the tokens, and now let's go further and also add another language. Let's add Solidity. Attention, I'm not talking about Solidity compiled to EVM bytecode. Solidity directly, no compilation. Now that we have this, once the transaction is loaded, we have Solidity directly. And here it is. We can copy it, and we can deploy a new contract. There we go. We can then add the contract. We will add a mock USDC contract. Now, let's submit it. All right. So once this transaction has loaded, we have one more contract, the third one, all of them in different language, just like that. We have done it in a few minutes. All right. We can see once again that we have USDC, and what we're going to do is we are going to read our balance again and mint again to show that everything is working fine. And let's use 923, 314, whichever. Good. We're signing said transaction. It goes to the chain. We have the tokens. It doesn't matter that it's directly Solidity. It's gonna work. It has worked. We can check our balance now. All good. Now, let's also take before we also deploy classical EVM to show you that it works perfectly. Let's also take a quick look in the Block Explorer to show you how the contracts work. So if we look at the recent transactions, we can look at the recent contract call. For example, if we look, let's go ahead and look at this contract. All right, so basically, we can see the code of the contract. That's what I want to show. The code looks exactly normally. The only thing that is different than the normal code is that the first 4 bytes are basically the language ID, which is used to know in which language to execute said code. Now, let's go and see a transaction. Let's go and see yes, that one. Now, if we look at the transactions, for example, let's view the details of it. You can see that it's simply a usual transaction like any other transaction, nothing special about it. We have 2 arguments for minting. So, yeah. Now, let's go further and also add an EVM contract. We already have EVM on chain, obviously, so we won't add it. Now, we'll mark the contract as a classical EVM contract, and we will deploy wrapped ETH. We see the bytecode, and we go further to deploy it. We confirm. And boom, we have it. Now, let's interact with it real quick. And obviously, for wrapped if, we don't just mint tokens randomly, but we send Ethereum to get back wrapped Ethereum. So let's check our balance real quick. We read it, 0, and we can deposit 0.314 Ethereum, for example, or 0.2, whichever. And it goes to the chain, then we have it. And once the transaction is done, we can look at the balance. We have the wrapped Ethereum. If we go now up to see, you can you go to another page and or like this. You can take the address of the contract from the Explorer. All right. Go and copy it. And we can go back, and we can basically see that the balance of the address has changed. It has actually received that Ethereum, and my Ethereum has been depleted from my account. And we can also see the balance of the contract on the Explorer real quick. All right, we can see the balance is 0.2 Ethereum. So it's this easy. One transaction to add a new language. Once we have its definition, then we just deploy contracts with a small, very simple change for all the developers in the world. And then nobody cares what language we use. It's all there, universal. Anybody can use it. Anybody can integrate it without changing their EVM-ready infrastructure. Thank you, everyone. So now I'd like to give E the word for the next part of the demo.
Okay, thank you, Ovidio. So in our first part of the demo, Ovidio already showed you how we upload language semantics, deploy the contracts written in different languages, and use this interface to interact with the contract. Now you will have this question, right? Now I have a single blockchain contains of smart contracts written in different languages. Then, can they talk to each other, right? And so that means if I have contracts written in EVM, can I call a contract in different language? For example, a contract in Solidity. Will that work? This is the first question. And the second question is, if that works, as a developer of the contract, how hard it is for me to adapt to it? Do I need to make some changes to my existing contract and so on? So in the following demo, the swap demo, I'd like to address these two questions. So this is a very simple swap interface. I think most of you are familiar with. And I think this is very common to the DApp user. But the difference is that the contracts behind it, they are actually written in multiple languages. For example, in this demo, we involve the router contracts that is written in EVM, the WBTC contract that is written in Rust, the DAI contract is in Solidity, and the USDC actually is written in our own simple language. Maybe, Chenlong, can you open the Explorer? Let's see, for example, this is the router contract, and we have a small tag showing the Explorer saying that what language this contract language is. So this is the router contract, and now this is the BTC contract, and you can see this is the Rust version. And now let's do some simple swap. And now we are swapping from 1 BTC in Rust to 80,000 DAI in Solidity. Let's do that. You first approve that, and then you will pop up the swap MetaMask and then allow you to swap. So I think from a user perspective, everything is similar. Everything are the same as you interact with the EVM chain. Now you can see the balance is increasing and so on. So let's go to the Explorer and see what actually happens. So you copy this transaction ID and throw it to the Explorer. I think the Explorer experience is also similar to what we have for the EVM. The only difference is that from the contract address, you can show the language tag to the contract address. And from here, we can see that you are interacting with this contract address, which is written in EVM. And now we are having some token swap, token transfer from the user account to the pool account. That happens in the BTC contract, which is written in Rust. And then from the pool address to user account, which happens in the Solidity contract. So that shows that contracts written in different languages can actually talk to each other through our ABI encoding. And since ABI encoding provides this kind of uniform interface for different languages to talk to each other, then we actually have minimal change to our language contract to talk to each other. When I say minimal, actually this is 0. Basically, if you go to the contract that we deployed for the router, can you show actually the source code of the router? So this is the actual source code of the router. Unfortunately, we don't have the time to actually upload the contract and show you the Explorer. But trust me, this is what we actually deployed on-chain. Let's go to the place where actually transfer happens. As you can see here, this is calling some ERC20 contract, and you still use this transfer interface to do the transfer. And the EVM semantics will just encode all core data in the ABI encoding, and the semantics of those Rust will handle the decoding of this core data and invoke the corresponding program to execute. So as a contract developer, you don't basically need to change anything. You just trust, right? The ABI encoding and decoding will do everything for you. This also applies to developer of the ecosystem like the tools of the Explorer and so on. As long as the tool respects this ABI encoding, you basically doesn't need to change anything. For this Blocks Explorer that we showed, right, because those transfer events and so on, they depend on the logs, which respects this ABI encoding, they can be displayed naturally on this Explorer. So everything is unified, and this provides a very seamless developer experience for the user as well. So I think that concludes our demo for the swap, and I will transfer the topic to Xiaohong.
Thank you, thank you. So we've shown you 2 demos. Go to the next slide. Right, so just to conclude, so what you see here is how we break the language barriers in the current Web3 ecosystems, right? So we really want to engage, all the Web2 developers. It doesn't matter what languages they like to use. We want to allow them to write smart contracts in any programming languages and allow those smart contracts to interact with each other. And they can all modify the same blockchain state. So last but not least, please do follow us by scanning the QR code here. So this is a link to our developer portal. So all the materials, the demos, articles, all the future news will be published there. So please follow us. And we are going to have another session by our CEO, Grigori, later today. So if you want to attend, please scan the QR code. And that concludes my presentation. And thank you very much.